Hi, everybody. Welcome to second day of IGDC, afternoon presentation. I hope you're all loading up on coffee and awake because we'll be talking about AI again, of course. My name is Max Kiehn. I'm a senior fellow at software development at Advanced Micro Devices. And what I'll talk about today, rather than how to use AI to generate game scenes, or sort of optimize games. What I'll talk about is how we apply AI internally to actually develop and test software, so that these games can run efficiently. Before we jump into the main topic, let's take a quick look in terms of how the software development evolved over the years. And if you take the experience of programming your first game, what a child, a teenager might do, well, in the 70s, you would have started with a programmable calculator. Anybody remember this thing? There was a game, nice. There was a Moonlander game, if you remember. You had to land a rocket on the moon with limited fuel and just thrust controls. And it was pretty challenging. But what was more challenging, actually, imagine programming that game on that calculator. You had to enter the hexadecimal instructions into the thing, and you didn't have really any other tools other than sort of the small screen on the calculator. So it probably takes several days to develop a program like Moonlander. But then, of course, in the 80s, we had personal computers. So now you had a keyboard, programming language, and you actually visualize the whole thing on the screen. So it's probably, would take you a few hours to be able to develop a simple game. Then, of course, in the 2000s, you didn't have to write code anymore. You could just drag blocks around and create the logic that you wanted and visualize it on the screen pretty much right away. So that will take a couple of hours to program the game. Well, with ChatGPT, you didn't have to do any of that. You could just ask it in plain English. So I'd like to generate, or any other language, generate me a source code for a Moonlander game, and now it came with a complete program that worked. And of course, you can actually do it on a phone without ever touching any other computing device. And of course, since then, the experiences are even more complex, so you can generate describe much more complex environments and still be able to generate. So the experience of programming the first game really transformed over the years. But now let's take a look at what happened to the large-scale software development, so large games or the graphics driver. Well, in the 70s, there was a lot of Fortran, COBOL code, and that allowed us to write a lot of code. Then in the 80s, we had more powerful languages, C, C++, and we wrote even more code. Then in 2000, we had managed runtimes, Java, C#, IDEs, which allowed us to write more code. And now, these days, we have huge data centers, machine learning frameworks, even more powerful languages, and ultimately, it allows us to write more code. And so we have to ask, what will happen 5, 10 years from now? Are we still going to be writing more code? So will anything change in the world of large-scale software development? So that's the question we'll try to answer. But before then, we'll talk a little about AMD and where we see applications of AI. Then we'll go through a couple of examples where we apply AI in testing and development. And then to talk about what we see happening down the road. Well, AMD is synonymous with high-performance computing. It's pretty much impossible to go through your day without touching AMD technology somewhere. Either it's a Ryzen CPU or Radeon GPU in your desktop or laptop, or one of the data center products or the networking that you use when you use online services. And AMD is at the frontier of innovation in all of these areas. One, of course, most important ones is graphics. And so AMD graphics is in desktops, laptops, workstations, gaming consoles. It truly is everywhere. And it's pretty easy to think about AMD as a purely hardware company. But the thing is that to make all that hardware pop, right, you really need a lot of software. And so that's where the AMD Software Adrenaline Edition comes in. You can see the scale of it. So even just this year, we had over 65 million downloads. on dozens of game features introduced, hundreds of products supported. Of course, what it matters is the day zero support for dozens of games, and not just support, but really optimizing it for the best, sort of most realistic, most immersive gaming experience. And of course, a lot of it comes down to the many features that Adrenaline supports in terms of that allows us to optimize the game, maximize the performance, dynamically adjust frame rates. And with that comes a lot of complexity. So when we talk about supporting a game or application, first of all, we have dozens of them to support in many different settings. But it's not just that game, of course. We need to worry about the support of all the AMD software, the graphics drivers and different features within it. Then, of course, we need to support multiple generations and different products, from the DGPU to APU. So it becomes sort of even more complicated. Then, of course, we need to test it on multiple displays and make sure it works with other peripherals. So it becomes even more complex. And then finally, it needs to work on multiple operating systems, Linux, Windows, and the consoles. And all of these things are changing all the time. So at the end, you have a very complex or rapidly changing ecosystem that we need to support in order to be able to deliver sort of these experiences. So that's where we really need AI. But what is AI? Well, the simplest explanation is AI is giving machines ability to reason plan like a human would do, right? But the key is that it does to do so without actually explicitly programming AI to do it, but making it learn from data and patterns in the data. Broadly speaking, there are two different types of AI, predictive AI and generative. So predictive, or also what's called old school machine learning, the goal is really to label a data point. So, for example, if you have images of cats and dogs, you want to be able AI to pick out, is it a dog or a cat? So it learns the decision boundaries are between the two. Generative AI, on the other hand, so you're actually able to generate a new image. So let's say generate a new image of a cat. So, but ultimately, both of these come down to data. So, and that's what we'll touch on. Well, the first application we'll talk about, and this is a gaming conference, of course, so it will be gameplay testing. Well, as fun as it is for somebody to sit and play games, it's really just not scalable. So with so many different configurations that we need to test, we really need to automate that process with the help of AI. And whenever thinking to apply an AI, what you should do is really understand how do humans do the same job. And if you look at a tester workflow, so the first step is install, provision the system, configure the game with the different settings that you want to test, then of course go through the game scenario, watch for any issues, and then collect the data from any issues that you're able to find, and then send the issue to be triaged and debugged by developer. And while most parts of this workflow are already automated, where we see AI helping is really with automating the gameplay itself and detecting any artifacts on the screen, so display corruption, what we call it. So let me talk about that first. Detecting screen artifacts is pretty challenging, and the reason for that, as you can see, there are so many different types of it. While some of them are fairly easy to detect, you have, for example, half of the screen being black, others are not so easy to detect. And there's no single algorithm that has been created that's able to capture all of these, and it would be computationally prohibitive to run it anyway. So we really need AI's help to be able to learn from this data. But how do you teach AI to detect anything on the screen? Well, first, we need to start with a simpler problem, image classification. Well, simpler in a way, I guess. So if you look at this image, what do you see? Well, I put a label there, but yeah, it's a cat. Even though you don't see the whole image of the cat, that's actually the image my daughter took of our cat a couple of weeks ago. But even though you don't see the whole image, you still see that it's a cat. As humans, we are able to isolate and understand the image. But how do you teach AI? AI just sees pixels. So the approach that's been proven very, very successful is taking a very large data set, millions of images, okay, different angles of the cats, different types of cats, and then dogs, of course, and other types of images, and then running it through what's called a convolutional network, and very deep, so with several layers. And what happens is that at each layer learns to detect sort of progressively more complex features. So the first layer may learn to detect simple lines or colors. Later layers, may detect more complex shapes like circles or parallel lines. And then final layers may be able to detect or activate on particular shapes like a wheel of a car. But of course, that's not our job. We need to teach AI to detect screen artifacts. And so what we do is sort of this approach called transfer learning or fine-tuning. Okay? Basically, we take a much smaller data set of the images with screen artifacts and without, and we retrain only part of the model. So we keep the basic features that the model learned, but we retrain the later part of the model so that it can learn what we are asking it to do. And so this approach, of course, is also very successful. And again, the goal here is to classify any images without having a reference. We don't want to maintain a huge database for every game title or every possible combination that we test. This doesn't need a reference to be able to tell whether there is corruption or the artifacts in the image. Well, whenever you train a model, how do you actually know that it works well? You visualize it. So this is a simplified plot of the model output, where the green dots represent images without artifacts, and then red dots those with artifacts. And what you want to see is a clear separation, right? So that the model has learned the decision boundaries of blue line. And that's exactly what we see here. You want to see clustering too, because there are different types of images, so the model has learned that as well. But occasionally you do see the green dots and the red dots on the wrong side of the line, and that's because AI models are inherently probabilistic. But as you can see, the model performance, I won't go into the detail explaining them, but the model is very, very precise, so it doesn't make false predictions about where there is corruption in the images or not. Okay, so now we have a model that's actually able to detect artifacts. Well, next step is actually we need to automate the gameplay itself. And it's good to kind of break down sort of what are the different tasks in the gameplay that need to be automated. Well, L0 and L1 are more sort of manual testing, sort of provisioning of the system, so that's already done. But then L2 would be actually configuring the game menu, so all the settings that we need to make sure that and test out. L3 would be more predefined or scripted gameplay where the character sort of has to navigate what you already know ahead of time. But then L4 and L5, this is where there is interactive gameplay. You're able to react what's happening on the screen and ultimately actually complete certain objectives within the game. And the difficulty for us, of course, is that for any of these tasks, we don't have access to internal game state, right? So this is key. All we have to go by is the images that we see on the screen. One other note is that the goal of this automation isn't really to overcome or exceed human performance. This will not be able to play competitive Apex Legends or a single-player game to compete with a human, but the idea is that it's still sufficient for us to be able to play test through the games. And there are a number of technologies that are needed to enable that. So for menu configuration, you really need to be able to understand the text. And there are actually, of course, technologies out there in the market that are well established, for example, optical character recognition, so that's the general area. However, the models, they actually don't do very well on the gameplay images because the text is highly stylized, there are different backgrounds, so you can't just really take an open source model and apply in this case. So what we need to do is apply several steps where we segment the image, isolate the text, and run it through our own OCR model to be able to detect it reliably. Well, for predefined gameplay, one of the simpler things to do. So if the game has a minimap, so you can just have the character follow that minimap. You don't need to necessarily interact with the environment. All you have to do is sort of decode the minimap where the character is facing and follow the path. There are different approaches for this. One of the more successful is what's called reinforcement learning, and that training an agent to be rewarded, okay, when they achieve particular objective. So let's say as the agent progresses through the path, and it will randomly try different things, but when it progresses, it will actually go towards the objective that's displayed on the minimap. Well, for interactive gameplay, you actually need to understand what's happening on the whole screen. So that's where, you really need to be able to detect where is the player, where are the different NPCs, where are their enemies on the screen, understand the scene, and make the decision, sort of, what do you need to do? Maybe do you need to engage the enemy, okay, or follow the NPC? And the key technology here, of course, is image segmentation. So be able to isolate the particular areas, recognize, okay, so whether it's an enemy, let's say, or an NPC, and be able to act on it. And finally, for L5, what you want is a goal-based playthrough. So it's not always that you want to complete the in-game objectives like a human. Sometimes you just want to explore as much of the environment as possible so that you can hit all the different areas. Other times you want to hit the areas which are sort of more stressful for the GPU, so we can, again, test out those particular areas. And here again, so there's a mix of reinforcement learning, so rewarding the agent for exploring new areas, for example. And we're also starting to make use of visual LLMs, so visual large language models, to be able to understand, all parts of the workflow, understanding segmenting the image, and then actually being able to help, with the playthrough. So how does it all come together? Well, instead of somebody sitting and watching the screen or you're playing the game, now most of the workflow is automated. So after the game is started and captures the video output from it, all the aspects of gameplay are automated, and the captures are run through the different models, right? So we have several models. One is for the frame detection, what we just talked about, but also we're capturing the full video, so we're able to detect issues like stutter or frame drops because we have the full access to the sequence of frames. Same for the audio detection. We're actually looking at the spectrograms from the audio recording to be able to detect if there are any audio issues. And then at the end, all of it is analyzed and the pass-fail decision is made. And the only manual test is really for the tester to be able to review anything that's flagged by this workflow as a failure. And as you can see, so this approach has been very successful. There is a mix of technologies, but over 100 different game tiles have been automated, and it's running on several hundred test machines. Because the whole process can run 24/7, so we're talking tens of millions of images or video frames being processed by this. Well, now you found an issue. Well, what do you do with it? Again, if we want AI to help, we really need to understand how the developers look at the bug reports, from testing. And first, developer needs to understand what is the issue, right? So maybe reproduce it, analyze the test logs, triage and debug. Then, of course, once they understand what the issue is, then they actually resolve it and test out that it has indeed fixed the issue, update any internal docs, and then push the code changes to the source control system. Well, you'll see that out of this whole workflow, coding is really just a small part of it, right? Understanding what the issue is quite often takes actually the most time. And so we see AI being able to help across all of these areas. Understanding where the problem is, triaging and debugging, and then fixing the bug itself. So one of the very first generative AI applications we deployed within AMD is engineering chatbot, and it helps developers understand issues and find answers. So when a user asks a question, we perform a search over the internal AMD documentation, any kind of prior issues or the docs on particular triage areas, and find the relevant context and then send that to the LLM, to the model to be able to answer. And this works remarkably well, okay? It works well because the models are able to learn from the context, okay? Now, you may be asking, sir, well, why are you not training the model here? Well, to understand that, let's look at what large language models actually learn. And fundamentally, they learn to predict the next word. Right? So if you type in to ChatGPT in the completion model, LLMs predict the next. Most of them will come back with the answer word. Right? So they're incredibly good at predicting that. But the problem is that the more complex the context, okay, the longer so the more they're prone to what's called hallucinations. Okay, and so basically making things up. You make a wrong prediction at one point, the next one tends to be wrong as well. They're also not able to cite their sources, so the kind of black box behavior. And they also lack kind of fundamental human reasoning, right? They have some very simple reasoning over particular areas, but you can't expect it to think like a human. They also suffer from having limited knowledge and domain expertise. Like, for example, it doesn't know anything or much about graphics drivers. And so to overcome those limitations, the first thing you want to try is what's called prompt engineering. And basically what you want to do is give the model as much instruction as possible to be able to act on the information. So you want to tell it, okay, what role is it playing? So if it's a question about programming, you're an expert C++ developer. If you don't want it to make things up, so you can instruct it to use only the provided context, okay? And that's what the chatbot does. It instructs it to do so, inserts the right context, and so that's sufficient to work in most cases. But prompt engineering can only take you so far, right? You still need to apply other techniques for more complex scenarios. So first of those is fine-tuning or training your own custom model. So AMD partnered with GitHub to train a custom model on our source code. And that allowed tools like Copilot, right? So where a developer can actually go into IDE, describe a problem that they want to solve, particular functions, so generate a unit test. And then Copilot would take the relevant context, find it in the open source files, and then send it to the model to generate. Well, the standard models didn't really work well for us, especially in for hardware engineering, languages like RTL and Verilog. But the custom models that were trained on our source code, they actually worked much, much better. All of this, of course, has to pass through what we call AMD AI proxy, where we're capturing all the inputs and outputs, and we're keeping track where all this generated source goes, both for legal reasons, but also for metrics to be able to measure how much impacts all these tools and different models are having. But ultimately, you can't ask Copilot, even with a custom model, to say generate a complete graphics driver. No model can do that. So we need something else. And what we need is agents. If you think about the standard workflow with an LLM or ChatGPT, you ask it to do something and it generates it in one flow. So that was called a zero-shot workflow. But humans don't work like that. If you want to write something or write a program, you would normally build it and iterate on it. So you would review, revise, and go in circles until you actually have something that you like. And that's what's called agentic workflow. It does improve the LLM performance, so just asking it, the model to think about what it's doing and reflect on it quite often improves the performance. But you can extend it even more. What if you could actually teach the model to operate certain tools to think like a developer? So for example, if you have a test log and you know how to analyze it, you can actually give it a tool that's able to parse through the log, provide the advice, or isolate the issue particularly. So say, okay, it goes into a different part of the code, or the problem is likely isolated to this component. And this is, of course, just one example. So you can add multiple tools and different agents as part of this workflow to be able to complete really complex scenarios. And when you put it all together, the workflow, so in this new world, is when a bug report comes in, it doesn't actually go to the developer. It goes through this workflow first. You're able to search code, docs, and issues. Maybe this issue already occurred, and you can just find a fix for it. You can find the relevant documentation. Maybe there is a debug and triage procedure. So again, you find it based on the bug report. Once you have that information, you can actually invoke the relevant tools. So if there is a log, so you can analyze it. If there's a procedure you found, you can apply it to whatever data you've already been able to collect. And the tools here could be log analyzers, debuggers, profilers for any kind of performance issues. Once you have that information, then you can actually start generating code. Okay? And it's not, again, a single shot. You want to be able to generate code, review it, okay, and let the agents actually evaluate it and build it. Because ultimately, the goal of this whole process, in this example, is to fix a bug. So if there is a test that actually finds the issue, you want to be able to rerun the test and it no longer finds the issue there. And so it usually takes a few cycles, for any kind of issue to be able to generate correct code that compiles and solves the issue. And then after that's done, so then you can actually generate documentation, updates, or any kind of pull requests submitted to developer. And what developers receive is a complete fix or a proposal for a fix, and they can review it and actually chat with the solution. So they don't necessarily need to accept. They can actually send it back, provide some feedback about what the model needs to fix. And this process can be triggered and so repeated multiple times. So the role of the developer really changed from having to go through all those steps, a lot of them didn't have to do anything with coding, to reviewing it at the end, so the end product of this whole workflow. So we have several tools already deployed in this workflow. So there is the chatbot, the copilot, some of the issue types are using this type of workflow, and several thousand engineers using different tools. The chatbot already answered over 500,000 questions, and so approximately a third of all the changes contain some kind of AI-generated code. So we're definitely seeing the early benefits, okay, or the impact of these tools. So that's great, but what happens in the future? Well, the paradigm of software development is getting transformed. So from let's say architects and PMs, so sending requirements to developers, and then they're writing something, sending it to testers. The new paradigm will be that instead, all the inputs, the requirements, designs, actually going to the software engineers, so the coding and testing agents. And then they will happily produce something, iterate in it. It's not just the code, it's the test, it's the documentation, so it's the full product, okay, that's needed to validate that the new code meets requirements and designs. And then that's when developers and testers would plug in. Any issues that are found can be actually triaged more efficiently. Developers can provide feedback, and then so this whole loop can be repeated until everybody's happy with the outcome. And we think that this will solve a lot of the time that developers spend, on non-coding tasks, and save developers a lot of time. And I guess one question is, what are developers going to do at that time? Well, they're probably going to write more code, right? They're going to be very creative. So the answer to the question we posed in the beginning is that yes, we probably end up with more code, but it's able to solve much more complex problems down the road. But what impacts is it going to have on the gaming experience and how we approach it? Well, what this graph shows is the cost of running a GPT-4 quality model, the cost to compute to run it. GPT-4, if anybody doesn't know, it's a frontier model, state-of-the-art, usually used as a benchmark. And it was released in March 23. It didn't exist before, but it probably taken several $1 million to run it, a year or two before. When it was released, the cost of compute would be about 100,000, and not to train it, just to run sort of an answer, being able to what's called inference. And the model itself was kept improving, but also the cost of compute kept decreasing. So now, actually, you can have a workstation class PC with several GPUs that's able to run an open source model, okay, with the GPT-4 quality. And then down the road, we actually see that costs continue to come down. So sometime next year, possibly even, and definitely later, the gaming PC, so of course it would be first enthusiast gaming PCs, that will be able to run these models, right, in parallel, so let's say with running a game. And what this will enable, sort of, a lot of experiences for the game itself. So rather than generating content when you are working on a game offline, you may be able to actually generate content dynamically as you play. So you may have much more adaptability to what a human player is doing. You may be able to generate some of the assets, during the game, again, based on what the player is doing. And ultimately, of course, that will create a lot more complexity for us, for AMD, to be able to validate so that we are continuing to deliver the best sort of gaming experience. So it will add a lot of complexity in testing and development for us because of the sort of the unpredictability and indeterminacy of the environment is rising. But also, what it'll enable us to do is all the use cases that we talked about, so being able to detect issues on the fly, maybe even sort of triage and fix them. Imagine sort of potentially being able to find an issue and then the solution is automatically suggested to you, or it even takes action to resolve it right away, so you don't even have to worry about it. So a lot of these experiences, I think, will be enabled as the compute will become more and more possible for these models. So we think definitely the gaming experience and so what we can do with it in terms of the graphics will really be transformed over the next few years. And AMD is actually in the unique position for that because of the broad portfolio that we have with the CPU, GPU, and NPU to be able to take advantage of the models and still be able to run the games. But this transformation won't be easy. It'll be very, very challenging, and so we really need your help to help make it happen. If you have any models, tools, or automation approaches to help us, deal with this indeterminate dynamic environments that you are working on, we'd definitely be able to take advantage of that, and so we'd like to hear from you so that we can bring about this transformation sooner. All right, well, thank you very much. Please don't forget to attend the Game On event on this weekend. There will be booths, with PCs set up, AMD hardware you'll be able to play and enjoy some computing technology and maybe even get one of these cool shirts. All right.
Well, that does sound tempting, Max. Guys, do we have any questions for Max?
Hi, very thought-provoking session. Thank you for that. I have one question on the agent building workflow. So do you have any homegrown solutions that you use for building the agents, or do you go with open source technology stack like LangChain or something for that?
Yes, we do use LangChain so the parts of the chatbot application are based on that. And for the frameworks, we do currently use, let's say, AutoGen, okay? But these are very early days, so the whole landscape of the different frameworks is still being sorted out. Ideally, what we would like to get, and that's probably what's going to happen, is that we don't have to reinvent each agent from scratch, right? So the agents, actually, the frameworks will come with the basic agents, with the ideally ability to take advantage of different tools or models as part of the workflow.
Thank you.